Hi, everybody. I thought we could take a look at filling in this Chapter 5, Assignment 61 in-class notes packet summary time. The first four problems are tone setting problems. They're here to get us thinking about using our calculus. And then much of the rest of the packet is about summarizing the stuff we're supposed to know. So let's take a look. Write a justification for the maximum. Well, if there's a maximum, I'm thinking about the first derivative. F prime of x equals negative 2x. And I know that negative 2x is never undefined, but negative 2x is equal to 0 at x equals 0, as the problem suggests. So if I make my f prime sign chart here with negative 2x, and I have my critical value of 0, and I test a number to the left of x equals 0, like negative 1. Negative 1 times negative 2 is positive 2, and therefore f prime is positive over here. If I plug in a number like 1 into f prime, 1 times negative 2 is negative 2, and therefore f prime is negative 2 over here. So I can see that f prime changes from positive to negative at x equals 0. And so my justification for this maximum would be there is a max at x equals 0 on, I wish I was right-handed, on f of x, because to the left of x equals 0, f prime is greater than 0, and to the right of x equals 0, f prime is less than 0. Okay. All right, next. Ooh, a piecewise has a minimum at 1. Well, let's just check to make sure that this piecewise function is continuous at 1. If I plug a 1 in here, I have negative 1 plus 1, which is 0. If I plug a 1 in here, I have 1 minus 1, which is 0. And since 0 equals 0, I know the limit of the function from both sides. That probably bears writing down. The limit as x approaches 1 from the positive side of f of x equals the limit as x approaches 1 from the negative side of f of x. So I know the function is continuous because that's also equal to f of 1. But is the function differentiable at 1? Well, if I write the equation for f prime of x is going to be also a piecewise function. The derivative of this piece is negative 1 for x values less than 1. And the derivative will be positive 1 for x values greater than 1. But at x equal to 1, notice the limit of the slopes won't be the same from both sides of x equals 1. We can say the limit as x approaches 1 from the positive side of f prime, that's the positive side, so that value is 1, doesn't equal the limit as x approaches 1 from the negative side of f prime, not of f, but of f prime. This value is negative 1. 1 does not equal negative 1. So we know the derivative doesn't exist here. This is a case not where the derivative is equal to 0 like the last problem, but instead where the derivative is undefined. So we're being asked to justify the minimum where the derivative is undefined. And my justification would be based on my sign chart. So if I make an f prime sign chart and I populate it with 1, and I check on this side of 1, I'm using this value. I notice that f prime for values less than 1 is a constant negative 1. So this is definitely negative. And over here, for values bigger than 1, the value of the derivative is always positive 1. Lo and behold, I have a sign change on f prime that goes from negative to positive, and so I know that f must have a minimum at x equals 1. And the justification sentence I write would be there is a min on f of x at x equals 1 because to the left of x equals 1, f prime is less than 0, and to the right of x equals 1, f prime is greater than 0. Okay? Now, these next two problems. If I think about taking the derivative to determine that there's a maximum at 2, ooh, a negative sign out in front. I think about this function as being written like this algebraically, and I think about taking the derivative by using that power rule. Not much of a chain rule problem, but definitely a power rule problem here. And I get negative 1/2 x minus 2 to the negative 1/2. Or, if you want to write it with radicals, we'd have negative 1 over 2 square root x minus 2. Well, in this form, it's pretty easy for me to see that when x equals 2, I'm going to have a 0 in the denominator. And I know then that this derivative, y prime, would be undefined at x equals 2. What about the derivative equal to 0? Well, I would set the numerator equal to 0 to find when this derivative was equal to 0, and the numerator is never equal to 0. The numerator is negative 1. So I'm thinking about just one critical number for y prime. But wait, what happens when we plug in some numbers and test? If I plug in a 0 over here into y prime, I get 0 minus 2 or negative 2. Can I take that square root of a negative number? No, that doesn't exist. This isn't a question of positive or negative over here. This is a question of existence. The function doesn't exist over here. So I guess what I'm really looking at here is the case where x equals 2 is an endpoint. This endpoint, the left endpoint. So when I check to the right of x equals 2 with f prime and put in, say, a 3 here, 3 minus 2 is 1, the square root of 1 is 1, 1 times 2 is 2, negative 1 divided by 2 is negative. And so I'm thinking about a left endpoint and then the function decreasing from there because the derivative of that function is negative. Well, if I had a function and it decreased from a point, I would know that point to be a maximum. And my justification sentence would be, there is a max on f of x at x equals 2 because x equals 2 is the left endpoint, and to the right of x equals 2, f prime is less than 0. You know, we could also understand this if we thought about it from a pre-cal perspective. Think about this square root graph being shifted to the right 2 places. What does this negative do on the outside of the function? This reflects the graph across the x-axis because I'm multiplying all the y values by negative 1. So I would be looking at a graph that looked like this. And notice at x equals 2, we have our high point, our maximum. Well, with this next problem, we've got just the square root of x minus 2. No reflection this time. So if I'm thinking about this graphically, I'm still shifting to the right 2, but my graph goes like this now. Is this a minimum or a maximum? Well, it's still an endpoint, and it's definitely the lowest point in its neighborhood, which is why I'm being asked to justify a minimum. Okay, so how do I justify a minimum at this left endpoint? Well, if I think about the derivative here, the derivative is going to be 1/2 x minus 2 to the negative 1/2, or 1 over 2 square root of x minus 2. There's y prime. Again, I get a critical value at x equals 2. Uh-oh. Excuse me a second while my computer falls asleep and I make sure that we're still recording. Yes, there we are. Okay. So we said that the derivative would be undefined at x equals 2, and the derivative is never equal to 0. So if I make my y prime sign chart and plug a 2, I know this is still the endpoint. And if I plug a value like 3 into y prime, not into y, but y prime, 3 minus 2 is 1, square root of 1 is 1, 1 times 2 is 2, 1 divided by 2 is positive 1/2. So I know that y prime is positive to the right of x equals 2. I have a function that is increasing after that point, so that point must be a minimum. And my justification for that point will be there is a min on f of x at x equals 2 because x equals 2 is the left end point, and to the right of x equals 2, f prime is greater than 0. Okay? All right, next question. Next question says, where can you find mins and maxes? Well, there are 3 places. F prime equal to 0, f prime undefined, and, as we saw in the last 2 problems, endpoints of a bounded interval. Okay. How do you know what the value of the min or max is as opposed to where it occurs? This is all about finding where the maxes and mins occur, but I want to know the value of the maximum, the value of the minimum. And this is found by plugging the x coordinates that we found up here, where the maxes and mins are, into the original function. This is what section 5.1 was all about, saying that if you want to know the values of maximums, you plug these possible candidates, these critical points and these endpoints into the original function, and you can find the relative values for those minimums and maximums. But really our sign chart is what helps us figure out whether each of those critical values turns out to be a min, a max, or neither. Okay, what about this last question on this page? How can you know if f is increasing or decreasing? Well, I think when f has positive slopes, f is increasing. And decreasing, well, I would say when f has negative slopes. Which brings us to the next page. What is the justification you want to explain when the function is increasing or decreasing? Well, if f is increasing when f has positive slopes, and f prime represents the slopes of f, then I want to say f is increasing when f prime is greater than 0. And so a justification sentence I might write, let's say, for example, that our function is increasing on the interval from a to b. I might say f is increasing on a to b because f prime is greater than 0 on a to b. And likewise, if I wanted to talk about f decreasing, then I would say that happens when f prime is less than 0. And so if my function was decreasing on negative infinity to a union b to infinity, I might then write f is decreasing on negative infinity to a union b to infinity because f prime is less than 0 on those intervals. Okay. How do you know when f of x is concave up or concave down by using f double prime? Well, f is concave up when f double prime is greater than 0, and I know that f is concave down when f double prime is less than 0. And what justification would I write? Well, let's say that, and I'm supposed to be using f double prime. So let's say I have this f double prime sign chart here. A and B and a plus and a minus and a plus. So I would say f is concave up on negative infinity to a union b to infinity because f double prime is greater than 0 on those intervals. And I would say f is concave down on a to b because f double prime is less than 0 on a to b. Okay, what's next? How do you know when f of x is concave up or concave down? By using f prime. Not f double prime, but f prime. Remember, f double prime represents the slopes of f. And so if up here we said f was concave up because f double prime was positive, what slopes must f prime have had so that f double prime could be positive? Well, f prime would have to have positive slopes in order for f double prime to be positive. And if f prime has positive slopes, we would say f prime increasing means f is concave up. When f prime is increasing, not f is increasing, but when f prime is increasing, that means that f is concave up. Because if f prime is increasing, we know then that f double prime would be greater than 0, and when f double prime is greater than 0, we know that f is concave up. Likewise, f prime decreasing means f is concave down because f prime decreasing means f double prime less than 0, which means f is concave down. So we can use f double prime to determine concavity of f, but we can also use f prime and whether f prime is increasing or decreasing to determine the concavity of f. Let's take a look at the next question. What is the justification you would write for function concave up, concave down using f prime of x? Well, to use this case up here before, where we saw that f double prime was positive and then negative and then positive, that would be f prime is increasing, b decreasing, and then increasing again. This positive f double prime corresponds to an increasing f prime. So if we know that there's this inflection point at x equals a, because f double prime goes from positive to negative, we could now say there's an inflection point at x equals a because f prime goes from increasing to decreasing. And so I would write, there is an inflection point at x equals a because to the left of x equals a, f prime is increasing, and to the right of x equals a, f prime is decreasing. But I also have this inflection point at b, and so I would say there is an inflection point at x equals b, not on f prime, not on f double prime, but on f of x. Okay, there's an inflection point at x equals b on f of x because to the left of x equals b, f prime is decreasing, and to the right of x equals b, f prime is increasing, period. Oh, sorry about that. Here, let's get that oriented for you. Okay, there's an inflection point at x equals b on f of x because to the left of x equals b, f prime is decreasing, and to the right of x equals b, f prime is increasing. Okay, so that's the way I can use f prime to justify inflection points on f of x. What's next? Well, it says, how do you find inflection points on f of x? Well, I guess I can think of two ways. These are places where y double prime changes sign from positive to negative or negative to positive. Y double prime changes sign, or two places where y prime goes from increasing to decreasing or decreasing to increasing. Okay, and if we think about a y prime graph for a moment, here's y prime. Y prime is increasing, and then y prime is decreasing. This point here is where y prime goes from increasing to decreasing. Well, we said a place where y prime goes from increasing to decreasing. This place is an inflection point on y. This turns out to be a max on y prime. So a max or a min, that's where y prime goes from decreasing to increasing. A max or a min on y prime can be an inflection point on y. Okay, what is the justification you would write for an inflection point at x equals a using f double prime? I would say there is an inflection point on f of x at x equals a because there is a sign change at x equals a on y double prime. Or you could say because y double prime goes from positive to negative or negative to positive at x equals a. Okay, There's an inflection point on f of x at x equals a because there's a sign change at x equals a on y double prime. Or we could say there's an inflection point on f of x at x equals a because y double prime goes from positive to negative or negative to positive at x equals a. All right, beginning of the second page. What do we have here? We have, what is the justification you write to justify inflection point at x equals b using f prime of x? Well, we talked about that. We said there is an inflection point at x equals b on f of x because f prime goes from increasing to decreasing or decreasing to increasing. Okay, how can you use f prime of x and f double prime of x to determine whether or not there's a min or max at x equals a? Well, this is the other second derivative test. And what does the other second derivative test tell me? Well, it says if f prime of a equals 0 and f double prime at a is less than 0, we know f is a horizontal tangent. F has a horizontal tangent. And we know from this piece of information that f is concave down. We're looking at something like this at x equals a. And so we would say there is, if f prime equals 0 and f double prime is less than 0, then f has a max at x equals a. All right, but what about a min? Well, for a min, we would want if f prime of a were equal to 0 and f double prime of a is greater than 0, then we know we're thinking about something that looks like this and something that therefore has a minimum. So we would say if f prime of a equals 0 and f double prime of a is greater than 0, then f has a min at x equals a. Okay, what's next? When looking at the graph of f prime of x, what do we know about f when f prime is above the x-axis or below the x-axis? Well, if f prime is above the x-axis, then f is increasing. And if f prime is below the x-axis, f must be decreasing. When f is increasing, or when f prime is increasing, what does that tell you about f double prime? And what does that tell you about f? Okay, so I would say if f prime is increasing, then f double prime is greater than 0, and f is concave up. And if f prime is decreasing, then f double prime is less than 0, and f is concave down. Next, when f prime is decreasing, what does that tell you about f double prime of x? When f prime is decreasing. What does that tell you about, I guess I did that one already, huh? That's this one. Sorry. Okay. This is only about f prime increasing. We've done that. So now here's f prime decreasing. That's this. And we know, what does it tell us about f double prime? F double prime is less than 0. And what does it tell you about f? We know that f is concave down. Is it possible to have neither a min nor a max where f prime equals 0? Sure. Think about y equals x to the third. Perf. No, that's a terrible graph. Sorry. Let's try again. There. And there. So that's x equals 0, and this is y equals x to the third. And what can we say about the slope there? Well, the slope at that point is 0, but I don't have a min or a max at x equals 0. And if I think about the sign chart here for the derivative, y prime would be equal to 3x squared, and this is equal to 0 at x equals 0. So if I make a y prime sign chart, I'll put 0 on it. But if I plug in a number over here like -1, -1 squared is +1 times 3 is +3. And if I plug in a number over here like +1, +1 squared is 1 times 3 is +1. So I'm looking at a situation where I have no sign change on y prime, and therefore no max or min. We need to have a sign change on y prime or f prime in order to have a max or min on y or f. Okay, back of the second page. Is it possible to have an inflection point where f double prime is undefined? Explain why or why not. Include a picture. Well, our shark fin conversation, I think, is the answer to this question. We have an undefined first derivative here, and therefore the second derivative, because the first derivative was undefined, the second derivative can't suddenly wink into existence. The second derivative is also undefined. But we see this function as concave down and then concave up. We have a change of inflection, and that's our definition of inflection point. A point where the function changes from concave up to concave down, or in this case, from concave down to concave up. So yes, it is possible to have an inflection point when f double prime is undefined. Is it possible to have an inflection point at an endpoint? Well, that's not possible. No. We can't have an inflection point at an endpoint because, for example, here, I am concave down, but what about on the other side? An inflection point is all about changing concavity from one state, like concave down, to another state, like concave up. But if you've got an endpoint, you can't go past it, so you can never have an inflection point at an endpoint, whether that endpoint is the left endpoint or the right endpoint. Okay, some fill-ins. If f prime is greater than 0, then f double prime is positive, because f double prime represents the slopes of f prime. If f prime is less than 0, then f double prime is, well, again, f double prime represents the slopes, and if f prime is less than 0, oh, I take that back. Hold on a second. Let's go back. If f prime is greater than 0, well, if I draw an f prime graph, here's an f prime graph. F prime. Now, at this point, x equals a, I know f has a min, but what about f double prime? Well, I think it looks like f double prime, this must be increasing, and therefore I know that f double prime would be positive. But couldn't I draw this picture as well? Oh, if f prime is above, no, I could draw this picture. If f prime is greater than 0, these are both f prime greater than 0, then f double prime is what? Well, here f prime is increasing, and here f prime is increasing. Wow, it seems to be that f double prime has to be positive. But couldn't I have this situation? Here I'm thinking about f prime again, and I'm thinking about these shapes. These shapes. What if f prime, both above the x-axis, but instead of increasing, f prime is decreasing? Then I would say, oh, well, when f prime is above the x-axis, in these cases where f prime is decreasing, I want to say f double prime is negative, and therefore f would be concave down. So I don't actually feel like I can answer this question. I don't know is the answer to both of these. If you told me f prime was increasing, I could say f double prime is positive. If you told me f prime was decreasing, I could say f double prime is negative. But we're told f prime is above the x-axis. This is really telling me about f, not about f double prime. It's telling me that f is increasing and f is decreasing, not about f double prime. So I can't actually say anything for these two. Okay, what's next? If f double prime is greater than 0, then f is concave up and f prime is increasing. And if f double prime is less than 0, then f is concave down and f prime is decreasing. Next, when f is increasing, f prime is greater than 0, or I guess you could say positive. When f is decreasing, then f prime is less than 0, or I guess you could say negative. And then here we're told f prime is increasing. Well, if f prime is increasing, then we know f double prime is positive, and therefore f is concave up. And if f prime is decreasing, we know that f must be concave down because f double prime is negative. Okay, next page. What can you say is happening at x equals c in each situation below? Okay, so here, because f prime goes from positive to negative, we know we have a max at x equals c on f of x. And here, where f prime goes from negative to positive, we say we have a min at x equals c on f of x. What about this situation here? There's no sign change. F goes from decreasing to decreasing, or from decreasing to decreasing. Well, at these points, I have neither a min nor a max. So I would say neither a min nor a max, but maybe an inflection point. But they only asked about f prime sign charts, so I don't want to go there with f double prime. What can we say is happening to the left and right of x equals c in each situation above? Oh, so they're asking me to do justifications here. Okay, we can say to the left of x equals c, f prime is greater than 0, and to the right of x equals c, f prime is less than 0. And this is our justification for a max on f of x at x equals c. There we go. We would say there's a max on f of x at x equals c because to the left of x equals c, f prime is greater than 0, and to the right of x equals c, f prime is less than 0. Okay, what about for this situation? Well, on this one, we would say to the left of x equals c, f prime is less than 0, and to the right of, pen's run out. Hold on a second while I grab another. Of f to the right of x equals c, f prime is greater than 0. And this is our justification for the min at x equals c on f of x. Okay, next. What can you say is happening at f of c and f double prime of c on f prime of x below? Okay, well, let's see. F prime is going from increasing to decreasing. So that means f prime has a max at x equals c. But we know on f double prime, that would be positive to negative. So we know that we have a 0 or undefined at x equals c, and therefore that f has an inflection point at x equals c. And here, where f prime goes from decreasing to increasing, we know that f double prime would be positive to negative, and therefore we would know that f would be going from concave up to concave down, and so we would say an inflection point at x equals c on f of x. So what can we say is happening to the left and right of x equals c on f and f double prime in each case below? Okay, well, I guess I would say to the left of x equals c, f double prime is greater than 0, and f is concave up, and to the right of x equals c, f double prime is less than 0, and f is concave down. That's for this situation. And then for this situation, I would say to the left of x equals c, f double prime is less than 0, and f is therefore concave down. And to the right of x equals c, f double prime would be greater than 0, and f would be concave up, which points out here I was decreasing, and so f double prime would be negative, and this would be concave down. Sorry about that. And here, because f prime is increasing, f double prime would be positive, and f would be concave up. Okay, glad I caught that. Sorry about that. Again, because f prime goes from decreasing to increasing, we know there's an inflection point at x equals c, but we can also say that to the left of x equals c, f double prime is less than 0, and therefore f is concave. I'm sorry, to the left of x equals c, f double prime is less than 0, and f must be then concave down, and to the right of x equals c, f double prime is greater than 0, so f would be concave up. Okay. Next, what can we say is happening at x equals c in each situation below? Well, f prime is positive to this endpoint. So f would be increasing to a point. So I say there's a max here. And f prime is decreasing after x equals c. So there's this point, and f is decreasing. So again, I say there's a max at x equals c on f of x. What about here? Left endpoint positive. That means there's a point C, and after that point, f is increasing. So I know this point must be a minimum. And what can I say here where the function decreases until it gets to x equals c? I'm looking at a situation like this, and so I want to say that there's a minimum at x equals c. Okay, fill in the table below with as much as is appropriate. Yeah, so there's not a lot appropriate, as we discovered earlier, by knowing that f is greater than 0. If f is above the x-axis, I don't know if f is increasing or decreasing. I don't know if f is concave up or concave down. So I can't put anything in here. And that's why this says as much as appropriate. Because there's nothing I can say here, and there's nothing I can say here. But when f is increasing, f prime is positive. And when f is decreasing, f prime is negative. Now, I don't know anything about the concavity of f here, so I can't make any suppositions about f double prime unless I knew about the slopes of f prime. And just because f prime is above the x-axis doesn't mean f prime is increasing or decreasing. I don't know what f prime is doing except it's hanging out above the x-axis. So I can't comment on this and this. But if I know f prime is increasing, then I know f double prime is positive, and therefore f is concave up. And I know if f prime is decreasing, then I know that f double prime would be negative, and f would be concave down. Okay, so if f is increasing, f prime is positive. If f is decreasing, f prime is negative. And when f prime is increasing, f double prime is positive, therefore f is concave up. And when f prime is decreasing, f double prime is negative, and f is concave down. Okay, let's see where we are now. Tell the signs of the first and second derivative if you know the following. F is increasing at an increasing rate. That looks like this. So I know f prime is positive and f double prime is positive. F is increasing at a decreasing rate. That's this situation. So I know f prime is positive and f double prime is negative. F is decreasing at an increasing rate. That looks like this. And in that situation, f prime is negative and f double prime is also negative. But if f is decreasing at a decreasing rate, that looks like this. F prime is negative and f double prime is positive. Okay. Explain what we know about f prime in each of the cases below. F is increasing, so f prime is greater than 0. F is increasing at an increasing rate. Oh, increasing at an increasing rate meant that f, we saw it up here, f double prime is positive. F is increasing. Oh, I'm supposed to be talking about, sorry, f prime. So yes, f double prime is greater than 0, and that means f prime is increasing. So I know these things. Okay, if f is increasing at a decreasing rate, we know f prime is greater than 0, f prime is positive, and we know, because of this decreasing rate, that f prime is decreasing. What about, now that's not to say, look, this is this situation, right? It's not f is decreasing, f is increasing. That's why f prime is greater than 0. But because f is concave down, that's why we know f double prime is less than 0, because therefore f double prime would be less than 0, so f can be concave down. Okay, how about this one? If f is decreasing, f prime must be less than 0, or f prime must be negative. And what can we say if about f prime? if f is decreasing at an increasing rate? Well, we said before that f prime would be negative in that situation, so f prime must be decreasing. And then finally, f is decreasing at a decreasing rate. So we know f prime is less than 0, and we know f double prime is greater than 0, and so we're thinking f prime must be positive and f prime must be increasing. Okay? Okay. And that was it. Congratulations, you made it to the end in only 50 minutes. Have a wonderful day, everyone. Take care. Oh yeah, don't forget to send me feedback on anything I should do differently next time.